Alright, so today I'll be going through an exercise on the concept of probability density function for continuous random variable and discrete random variable in the context of data science. So first, before starting with the code, what exactly is a discrete random variable is? And the answer is that a random variable x is a discrete random variable if there are a finite number of possible outcomes of x, or there are a countably infinite number of possible outcomes of x. And to elaborate the second point, a countably infinite number of possible outcomes means that there is a one-to-one correspondence between the outcomes and the set of integers, and that's a definition of discrete random variable. Now let's start off with the code. First, with the discrete random variable, I will be building a plain vanilla Python function using NumPy and plot the bar graph of a discrete random variable with our code. So let's start off. First, let's start my Jupyter notebook. I'm within PyCharm IDE. And just in case if you do not know that to start off Jupyter Notebook, to integrate Jupyter Notebook running, so my Jupyter Notebook has already started running here in the browser, but to integrate that with the PyCharm, I need to copy this whole URL with the token. And get to my settings. Under build, execution, deployment, Jupyter server, select configured server and paste the whole URL here. Apply. Okay. All right, now whatever I do here in Python, that would that will be integrated with the running Jupyter NB. So Jupyter Notebook. Function.id. That. All right. Let's see if it is running. Yep, it's running. You can see that I can run the whole Jupyter Notebook with this icon here, run all, and the output is on the right side. I am going to need to render the graph of the discrete random variable function. I am going to need matplotlib, so import okay, I think I'm good with this. Okay, first I have to, here I'm going by the classic definition of frequency distribution oriented probability calculation for discrete random variables. So I need a function which will give me the frequency distribution of the sample values. So let's define one function. Oh, sorry about that. Oh, I need to get my keyboard shortcut keys remapped. Yes. Frequencies phi plus equal to 1. And I have to return the frequencies. All right, that's my get frequencies function. I need another function for calculating the probabilities given the sample data and also the frequencies. So probability is just in this case of a frequency distribution oriented probability calculation, the probability is just a number of times each value occurs in the sample. Now a probability frequency distribution need to be created, and for that I need a way to show how often an event will happen. It also shows what the probability of each event happening, and so basically it will be a frequency distribution table that will be formed conceptually. So let's start if sample data frequencies. Okay. That's an empty list. Frequencies. I'm just going to append the frequencies, that is the number of times it occurs in the sample. So that would be let's round this, round v, which is a value, and the length of the list data. Okay, let's make it one. Okay, my two functions are ready now. And just to give the background another time, that in my calculation of the experiment of the calculation for the probability, it consists of n outcomes, and it is reasonable to assign equal probabilities to all the n sample events. This kind of situation includes the obvious example of as tossing a fair coin or fair die once or twice, or selecting one out of several cards from a deck of cards, etc. So in this particular case, I'm assuming it's a coin flipping experiment that I'm doing. So let's go to the next step. I'm just manually creating a sample data, which is for the calculation of probabilities, which will be my sample, and my sample data would be, I'm assuming I'm tossing a flipping coin, a fair flipping coin, that is each of the outcomes has equal probabilities to occur. So I'm assuming that I will get 3 times heads and 7 times tails. So Let's define my sample data like this. For each of the head, I'm specifying it with each of the occurrence of the heads, I'm specifying it with a H string, and that would be my 3 times plus T. T stands for tails, of course. So the I have to get the frequencies from the sample data. So let's define another variable, calculator. Okay, and let's see what it prints for now here. Okay, you can see my sample space is an object with H 3 times and T 7 times of occurrence. Perfect, makes sense. Now the next stage. Now the probability calculation. This should give the probabilities PR. Why am I getting a TI? Yes, okay. As you can see, this should give the probability because it will take, this function will take the frequencies and the sample and calculated that each element of the sample divided by the length of the sample data, which is in this case is the probability for each occurrences. So let's print it and see how what it prints here. Calculated probabilities. And as you can expect that it gives me 30% probability for the heads and 70% for the tails. Okay. And let's now I want to plot it with matplotlib, so let's define the x-axis. Okay, before defining the x-axis, I need to get the unique values from the sample, and I can do that with set function of Python. Set. You want to plot a bar graph, so plt.bar axis calculated probabilities. Perfect. So the bar graph will show me the on the x-axis it will be the this list with taking the unique values only from the whole list, and the vertical column will be the probabilities. So okay, and to show it, I have to do plt.show. Cool. Let's run it again. Oh, just as I expected. Alright, so now let's start the second part, which is the same probability density function calculation for a continuous random variable. I'm creating a new file. All the regular import. Here I have to import SciPy, which is one of the most popular library for dealing with scientific calculation. Here I need to calculate the PDF of a continuous random variable, and for that it involves quite a complex calculation with integration. So we are not definitely fundamentally implementing that. We will be using a built-in function of SciPy. Let's define the continuous random variable first. It's quite important, and it's different than we defined the same for discrete random variable. So a continuous random variable differs from a discrete random variable in that it takes on an uncountably infinite number of possible outcomes, while for discrete random variable, which takes an finite or a countably infinite number of possible values, but here for continuous random variable it will be uncountably infinite number. So which means is that the possible outcomes could be infinite. So for continuous random variable, the probability that x takes on any particular value x is always 0, which is the main key differentiating factor between discrete random variable and continuous random variable. So we will come to this point later in this video, but first get some code running here. So to calculate the PDF or the probability density function, we first need the data for the x-axis, which is a sample of sample data. So I'll be using NumPy here. So let this be our idea. Let's give the start as 0.3, 1.75, and 500. So this linspace function, what it does is that this is one of the most often used function in data science in the NumPy space, and here I'm using it for creating a numeric sequence for the horizontal axis. So we will use this function to generate equally spaced numbers between start and end, and of course if you go to the documentation, I think I have the documentation. Yep, this is the documentation of NumPy linspace. It says that it returns an evenly spaced numbers over a specified interval, and so in this case I'm giving the start value as 0.3 and end value as 1.75, and I want a total 500 data points from this. So we can actually see what it prints. Distribution. All right, you can see it gives a long list of data, all are equally spaced, and it starts with 0.3 and ends on 1.75, both inclusive, and total number of data points are 500. Okay, let's delete this one. And now I need the actual probability, and here is where I will use a very famous SciPy function called norm.pdf. So let's define stats.norm.pdf. The first parameter it will take is the distribution, and then the location parameter, which in my case is 1 point. This parameter denotes mu, that is a mean, and the last one would be the standard deviation. Let's give 0.2. So a few words on this function. The stats.norm will give me a normal distribution, normally distributed variable, and the stats.norm.pdf, that is a PDF function. This calculates a probability distribution function for that normal distribution. Given mean, and standard deviation. So my mean here is 1.075, 1.075, and the standard deviation is 0.2. So specifically, it computes the value of the PDF at point X for a given mu and sigma. And okay, so yeah, that looks cool. Now we can actually plot it right now. Let's plot it. plt.plot. I need to provide the x-axis, which is distribution, and the y-axis will be the probability. Okay, let's run it. Cool. So we have plotted normal distribution function, and this is the PDF, probability density function. So a key point I wanted to discuss here about the PDF function here, that you can see that the peak of this is at 2, and which is which is obviously you can think that how come it become 2, because probability can never be more than 1. And the answer is that to understand the answer, you first have to ask another question, that does PDF, that is a fx function PDF, gives a probability? And the answer is no. PDF does not give you the probability, it gives a probability density. So the probability density's value at some specific point does not signify the probability, rather it signifies the density of the probability around that point. So it means how much probability is concentrated per unit of length near that point. And also this function that scipy dot, and so also this dot PDF function does not give a probability, that is the area under the PDF, but rather it gives the value of the PDF at that particular point, that is, for example, x that you pass to PDF as its argument, and that value can very well be greater than 1. And this is because remember that the PD in PDF stands for probability density, not probability. And density means probability per unit value of the random variable that can easily exceed 1. What has to be true though is that the integral part of this density function taken with respect to this value must be exactly 1. Normally, one analogy I normally try to give, and that is also for when I initially started studying about it, I understood it in this way, that think of it from a physics perspective. The probability density function is like the density of some compressible fluid, whereas its integral is like the mass. If you take a fixed mass of liquid and compress certain parts of it, you can make the local density as high as you like without changing the total mass. So here the PDF is giving the local density of a value through this curve. All right, so that was pretty much this exercise was about. Thank you very much for watching.